Welcome to EPG Pachala. I am Dr. Venusatini from the Department of Philosophy, University of Hyderabad. This is Logic 2 and the name of the module on which I'll be talking today is Invalidity, Quantifiers and Duality. The objective of this is twofold. One, apart from the usual truth table method for testing validity of arguments, we will propose a model semantical method for testing arguments involving quantificational sentences. Second, we will find a method of testing or demonstrating the truth of certain logical propositions which involve quantifiers. And how we are going to do that is by showing interdefinability of quantifiers, that means proving this interdefinability and then using it as a rule of inference for our derivation. So that is the objective. So far we have seen that there are different techniques and methods of checking arguments depending on different systems. For some we have used truth table, the common one, for some natural deduction system, for some truth tree and things like that. But the most important function in all this is to come up with tools, techniques for checking the validity of arguments. And in all these systems, the definition of validity remains the same. That is, if I can show that the premises are true, then it guarantees, the form of the argument rather guarantees the truth of the conclusion. Likewise, how are we to define invalidity? In each of the systems that we have mentioned or seen before, if only I can show that all the premises are true and yet the conclusion is false, then an argument is said to be invalid. We are going to use a new method, as mentioned right from the beginning, a technique called semantical model or model technique or model approach to test the validity of or invalidity of some arguments which involve quantifiers, that is quantificational propositions. And how are we going to do that? It is by this way. First, we will show the logical equivalence of simple quantificational sentences and truth functional compounds of singular propositions. Simple quantificational sentence will look like all Indians are humans or some Indians are women. What does a truth functional compound of singular proposition look like? For example, Sonia Gandhi is an Indian, Rajiv Gandhi is an Indian, Rahul Gandhi is an Indian, Modi is an Indian. A series of conjunction of singular sentences. Or the other could be either Rahul Gandhi is an Indian or Sonia Gandhi is an Indian or Modi is an Indian. A compound, truth functional compound of singular sentences or proposition. Let us proceed further. How are we going to technically show that these two things are equivalent? Then we will introduce something called universe of discourse. That means it is from this universe that we are going to introduce something called models. So how many kinds of entities or how many entities or objects are there in the universe? We will use that thing to show the equivalence of these two types of sentences. For example, if in our universe of discourse there is exactly or only one object, let us name it A, then we can show the equivalence of quantificational sentence with compound of singular proposition in this way. Quantificational sentence will look like for all values of x, x is p. It can be shown to be equivalent to PA. That is, we are assuming that there is only one entity, one object called A. And the second one is, how are we going to show the equivalence? It is of existential sentence with a compound of singular sentences. Here, if we have only one object, then actually even propositional sentences do not require truth functional connectives. So here, for some x, xp is equivalent to pa, but the difference will come out in the next one. Suppose there are two objects in the universe of this course, let us say a and b, then we can actually show simple quantificational sentence and its logical equivalence with truth functional compound of singular propositions like this. For all values of x, x is p is logically equivalent to pa and pb. Now it is a compound. And for existential statement, for some values of x, x is p is logically equivalent to either pa or pb. Likewise, we can suggest or come up with more models, which here let us say are a, b, c. So for all values of x, x is p is logically equivalent to pa and pb and pc. It is existentially equivalent to a truth functional compound of singular sentences in this way. There is an x such that x is p is logically equivalent to either pa or pb or pc. Likewise, we can come up with more and more models. That means we can come up with more and more objects in our universe of discourse. But every time we come up with more and more numbers, we can also expand our compound of such sentences. On the left hand side, it will always be the same. For all x, x is p. If it is existential, there is an x such that x is p. Left hand side same. But on the right hand side, our sentence will become longer and longer. If it is a universal sentence, then it will become pa and pb and pc and pd and blah 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 till pn. If it is existential, then either pa or pb or pc or pd and so on so forth, pn. Then actually, to put it in a broad framework, a universal sentence is satisfied by a series of conjunction of similar propositions, whereas existential sentence is satisfied by a series of disjunction of singular sentences. So assuming that our universe of discourse is non-empty but it is finite, we can always construct logical equivalence between quantificational sentences and truth functional compounds of singular sentences. Now, having said this, how are we going to show the validity of argument involving quantifiers? That is what we will try to do now. Suppose we have an argument. Let us look at these arguments. All Indians are humans. All Americans are humans. Therefore, all Indians are Americans. Obviously, we know that this is invalid. But there is a procedure, there is a technique to show the invalidity of this argument in logic. So, we will first do symbolization. The first sentence can be symbolized as, for all x, if x is an Indian, then x is human. Second premise, for any x, if x is American, then x is human. Conclusion. Therefore, for all x, if x is Indian, then x is American. Now that has been symbolized. How are we going to show the invalidity of this argument? That is by, let us say, supplying models. Let us say there is only one model in our universe of discourse. Then all these x can be replaced by a. Now we need to assign truth value. As mentioned earlier, invalidity happens when we can find interpretation. Rather, we can assign truth value f to conclusion and t to the premises. So, is it possible to show this way? Yes, it is possible. Now here, if we can only assign truth value f to conclusion, how are we going to show the invalidity of this argument? That is, we have to make the conclusion false. And given this sentence, how to falsify this sentence? Now the conclusion is a conditional sentence. So that means under the interpretation of implication, a conditional sentence will be false only if antecedent is true and the conclusion is false. So now we assign f, truth value f, to the consequent. Here the consequent is actually a means Americans. So now we have to assign t to all the premises. Now if you look carefully, then if we can only assign f to a and t to the rest of the sentences, this can be shown to be invalid, and we can actually do that. Now let us look at another arguments. For example, all Indians are rich, some Americans are rich, therefore all Indians are Americans. Suppose we have only one object in our model, then there is going to be some problem. By looking at the argument, we know that this is invalid. But if we have only one model in our universe of this course, we cannot show actually that this argument is invalid. Because there is no way you can assign truth value f to conclusion and t to the premises. You try, you cannot show. But this argument can be shown to be invalid if we have more than one model, and which is what we are looking at now. Let us do it with two objects, A and B. That means the sentence can be symbolized like this. If A means IA, then RA, and BI, then BR. That is the first sentence symbolization. Second, this is the second one is an existential sentence. So it will become a series of disjunctive sentences. So A and RA, or AB and RB. So from here we can symbolize the third sentence, which will look like this. Therefore, AI implies AA and IB implies AB. Now, to show the validity, rather to show the invalidity of this argument, all we need to do is to make the conclusion false. Now, how do we make the conclusion false? Because the conclusion is a conjunctive sentence. In which case, if we can show that one of the conjuncts, one of the parts is false, the whole sentence becomes false. So that means all we need to do is assign F to AA, the first part of the conjunct, then the implication, the conditional sentence become false. The rest we can assign T, means true, to all the other sentences, atomic sentences. So in which case we will be able to show that the whole premises is true and yet the conclusion is false. So if we have two models, then we can show the invalidity of these arguments. We have just done the first part, that is employing model semantics, using model instead of truth tables to show the invalidity of arguments. Now for the second part, which is to do with quantifiers, here by quantifiers we are actually looking at the interdefinability of quantifiers. This is important because if we can show that quantifiers are interdefinable in the sense that they can be shown to be equivalent, then we can use it as a rule of inference in much the same way as in the propositional logic. Logically equivalent expressions can replace each other. So if I can show that quantificational sentences are equivalent, then I can replace one by another, and then and this can be used as a rule of inference. So this is how we are going to do now. Show first interdefinability thesis, and then using as a rule of inference to show, or rather to check or demonstrate the logical truth of quantificational sentences. This is important because unlike other propositional logic, we cannot use truth table technique to check the truth of quantificational sentences. So this needs to be done. And the technique that we will do is a natural deduction system, which we have seen earlier. Let me just let us just have an example of what uh, uh, how to employ natural deduction system to prove the or to test the truth of certain logical sentences. In propositional logic, let us say if we want to prove the tautology of a sentence, if A, then B implies A. It's a logical truth. It's a tautologous sentence. How are we going to prove this one? Then it can be proved or rather demonstrated in this way. Let us look at the slide. We will begin with the assumption A. Now, the rule of addition says that if we have A, we can infer A or not B. That is allowed. So, given 1 and 2, we can now, by rule of conditional proof, we can move on to the next step. A implies either A or not B. And by the rule of commutation of disjunction, we can change the position of A or B, A or not B into not B or A. So, in the fourth, by material implication, that is a logically equivalent expression of disjunction and implication, we can derive A implies B implies A. So, we have shown that this sentence can be derived. Now, that is just to give us an idea of how the truth of logical sentences can be shown through natural deduction system. How are we going to use this with quantificational sentence? That is actually our challenge. And as mentioned before, we will first show interdefinability. That is logically universal sentence can be shown to be equal with existential sentence. How? That is, let us look here for a quick thing. We have just seen how in propositional logic we have used natural deduction method to test the truth of logical propositions. So also here what we will do is we will show interdefinability of quantificational sentences. Once it is shown, then you can actually replace logically equivalent expression by another sentence. We know this rule by the name rule of replacement in the propositional logic, and that is what we are going to do. But we will be able to use this as a rule, let us say rule of replacement, only if we are able to demonstrate the equivalence of this expression. So in propositional logic, let us look at the slide how we have done it. If we want to show the logical equivalence of P materially equivalent to Q, will be the case if and only if P implies Q and Q implies P. That means given two expressions P and Q, they are said to be equivalent even only if Q is derivable from our assumption that P, and P is also derivable from our assumption that Q. In other words, to show that for all x is P is materially equivalent to, it is not the case that there is an x such that xp is not the case. We need to do like this. We have to first show that for all x, xp implies it is not that there is an x such that xp is not the case. That is logical implication. And the second half is it is not the case that there is an x such that x is not p implies for all x, x is p. So that means if we can show double implication, then their equivalence can be shown. Now we will show the double implication. That is, we will derive first one part and then another part to show the logical equivalence. First part, for all x, x is p implies it is not the case that there is an x such that not px. We will try to derive this. So for derivation, we can have any number of assumptions. So we will have assumption 1, 2, 3. First assumption, there is an x such that it is not the case that xp. Second assumption, not PA. Third assumption, for all x, x is P. So we will try to derive our conclusion using these assumptions. So look at step number 3. For all x, x is P. By applying the rule of universal instantiation, we can get PA in the fourth step. Now, in the next step, by taking 3 and 4, we apply the rule of conditional proof. And we have for all x, if for all x, x is P, then PA. Now, look at step number 5 and step number 2. We can apply modus tollens rule, and then we can derive number 6, which is it is not the case that for all x, x is P. Now we need to discharge our assumption, so we need to do existential instantiation, which if when we do it on the step 1 and then 2 to 6, it looks as if we are reiterating the same thing. It is not the case that for all x, x is P. Now the next step number 8, we can apply conditional proof. That is 1 and 7 will give us step number 8. There is an x such that x is not P, implies it is not the case that for all x, x is P. And by law of transposition and double negation, we have the step number 9, which is what we want to prove in the beginning. For all x, if x is P, then it is not the case that there is an x such that xp is not the case. First half has been proved. Now let us move to the next part of the proof. We need to prove it is not the case that there is an x such that if x is not P, then for all x, x is P. We need to derive this. We need some kind of assumption. Here we will need two assumptions. First assumption, it is not the case that there is an x such that xp is not the case. Our second assumption will be not PA. Now look at step number 2. We can apply the rule of existential generalization and arrive at step number 3. There is an x such that it is not the x that x is P. Then by application of conditional proof from 2 to 3, we can come to fourth step, which is we have arrived here by the application of conditional proof 2 and 3. From 2 and 3 we can get if it is not the case that AP, then there is an x such that XP is not the case. By the application of rule of transposition, we can now have it is not the case that there is an x such that XP is not the case, then PA. From here, we can apply next rule, which is modus ponens, from step number 5 and step number 1. Given this, we can have step number 6, PA. Now we need to universalize. That means universal generalization. From step number 6, we get step number 7. For all x, x is P. Now we need to apply once more the conditional proof, the rule of conditional proof from 1 and 7, which will give us step number 8. It is not the case that there is an x such that if xp is not the case, then for all x, px. Now we have proved both the sides of a conditional sentence. Therefore, these two expressions have been shown to be equivalent. In other words, they are interdefinable. Now, given this, we can have a set of logical equivalent expressions. We have actually 4, which I will show them now on the slide. 1. It is not the case that for all x, x is P is equivalent to there is an x such that xp is not the case. 2. For all x, it is not the case that xp is equivalent to, it is not the case that there is an x such that x is P. 3. It is not the case that for all x, xp is not the case is logically equivalent to there is an x such that xp. 4. It is not the case that there is an x such that xp is not the case is equivalent to for all x, x is P. So these 4 will constitute what is called quantificational negation. I mean, this will be used as a rule of inference, and then as part of the justification, we will just use Qn. Qn means as a justifying principle. So with this, we can try to demonstrate the truth of some logical sentence. Let us move on to the next slide. Given those rules of equivalence, like quantificational negation, we can use these rules to demonstrate the truth of some logical proposition involving quantifiers. Suppose we have a sentence, for all x, it is not the case that there is a y such that x p y. That is our assumption. From here we can infer by quantificational negation. For all x and for all y, it is not the case that x p y. What we are doing here is replacing logically equivalent expression. In that, let us look at step number 1 and 2 as has been shown on the board. That the second part, not xy, has been replaced by y not, y negation. So that means existential quantification has been replaced by universal quantification, and the position of negation has changed. Third step, and look at step number 1. For all x has been replaced by it is not the case that there is an x such that there is a y and pxy. So by appropriate substitution, means rule of replacement, by appropriate substitution we are able to show that 3 is also derivable from 1. Let us take some ordinary sentences involving both universal quantifier and existential quantifier, and then see whether they are equivalent or not. For this, let us take this sentence: not everything that glitters is gold. And another sentence: some glittering thing is not gold. Now, how do we symbolize the first part, A? Not everything that glitters is gold. We will symbolize by saying that it is not the case that for all x, if x is g, then x is g prime. For symbolization of B, some glittering thing is not gold, we will say there is some x such that x glitters and x is not gold. Now, we will try to show that from A we can derive the symbolization B. So step number 2 says it is not the case that for all x, if x glitters, then x is gold. Now by implication we can change step number 2, which is it is not the case that for all x, it is not that x is g and gx is not the case. That is, I am trying to show that equivalence of implication and conjunction, and then appropriate replacement. Now fourth, by logical equivalence, which is quantificational negation, the rule we have just seen. In the fourth step, universal quantification can be replaced by existential. So for some x, x is g and x g is not the case, which is what we want to prove, that if we symbolize sentence B, some glittering thing is not gold, the symbolization will be, yes, it is not the case that there is something such that x is glittering and x is not gold. So in the fifth step we can show that they are equivalent. So this is how we can show the equivalence of quantificational, universal sentence and existential sentence. We are moving towards the last part. We will do another demonstration of logical truths. Suppose we want to show the logical truth of this expression. There is an x such that if x is p, then for all w p. For this, let us begin with an assumption. Assumption number 1 is how do we demonstrate the truth of this sentence for some x? If x is p, then for all w, w p. In propositional logic, we normally negate the sentence, and if it results in contradiction or it results in tautologos, then the truth of the premise is shown or demonstrated. So here let us begin with this assumption that it is not the case that there is an x such that if x is p, then for all w, wp. This is negation of the proposition, which is an assumption. Now from number 1, by applying the rule of quantificational negation, we have this sentence: for all x, it is not the case that if x is p, then for all w, p, w. We have replaced the existential by universal quantifier. Third, we need to do universal instantiation. So if we do that, we have it is not the case that if pa, then for all w, wp. The next is by equivalence of implication and conjunction. We have step number 4, pa and not w for all w, wp. So given this step number 4, by rule of another rule of simplification, we can come to 5, which is pa. From pa, we can apply another rule, which is universal generalization. We have step number 6, for all w such that w is p. Now from step number 6, we can apply the rule of addition. So we have either for all w, wp, or there is an x such that xp implies for all w, wp. Step number 8. Then by applying the rule of simplification from step number 4, we can get 8, which is it is not the case that for all w, wp. Now from step number 7 and 8, by the application of disjunctive syllogism, we have step number 9, that is there is an x such that if x is p, then for all w, wp. Here we are coming to the next step, that is by applying the rule of conditional proof. 1 and 9, we can have step number 10, which is it is not the case that there is an x such that if x is p, then for all w, wp implies there is an x such that if x is p, then for all w, wp. Next step is step number 11, by replacement of equivalence, that is implication. We have step number 11. So implication is to be replaced by disjunction. Double negation, there is an x such that if x is p implies for all w, wp, or there is an x such that xp implies for all w, wp. Here from here we can go on to step number 12, which is just double negation. So elimination of double negation, we get step number 12. Everything remains the same, and we move on to step number 13, which is just application of a rule of tautologos, because both the parts, that is disjuncts, are same. So in which case we can arrive at step number 13, which is there is an x such that if x is p, then for all w, wp. So we have demonstrated the truth of this sentence. In this module, what we have seen are twofold. First, by using the method of modal approach or modal semantics, we have tried to prove the invalidity of arguments involving quantifiers. The next one is by showing the interdefinability of quantifiers. We have generated n number of equivalents between these two quantifiers, and then use them as rule of inference to demonstrate the logical truth of quantificational propositions. Thank you.